The universe prolonged conclusively, encouraging altogether extra distinguished length after this era. It endured to grow, however, at a slower pace. In the end, converting into the universe we be aware today. This is the inflationary speculation of the vintage galactic blast, the most eminent and widely perceived hypothesis of how the universe started out. However, for a few physicists, this head hypothesis doesn't precisely portray the movement of our universe. They recommend that the universe existed earlier than that factor, extending on and on into the past as well as into the destiny. Even as the universe is extending these days, it changed into contracting before the Big Bang. In this view, the Big Bang is not a bang as a leap, a next when a contracting universe traded course and started to create yet again. As shown by their speculation, the universe may want to pass with the continued improvement, likely accompanied by a breakdown in the far future. Then one more leap. Numerous physicists proposed the jump will be never-ending. This challenges the norm cosmological view wherein everything began with a massive bang. The extraordinary physicist Brian Cox additionally challenges the hypothesis of how matters got here to be, declaring that something cannot emerge from nothing. Adding to the pressure, the James Webb Telescope has made startling revelations clashing with the possibility that the Big Bang can refer to the start of the universe. These brought up the query: if the large bang wasn't the beginning of the universe, then what turned into? Ought to the universe sooner or later begin with a skip or something completely extraordinary? The opportunity that the universe had a beginning or an afternoon without yesterday, as it became initially acknowledged, returns to George Lemaitre in 1927. Even as it is an imperfect circumstance to suggest that the universe probably had a beginning, that duration of galactic records has little to do with the new enormous bang that depicted our underlying universe. But exceptional space specialists or even a minority of experts nonetheless keep on with the conviction that the massive bang manner the very beginning of everything. All matters considered, the definition is obsolete. The Big Bang isn't the presentation of life as we might be aware of nowadays. In fact, there is tons proof highlighting a non-solitary starting of our universe. We never arrived at those conclusions based on no evident endpoint or excessive temperatures. Our universe is pleasant defined by using an inflationary length that passed off beforehand. The Great Bang is the result of what happened toward the consummation of development. During improvement, the universe changed into definitely void, no debris, regardless of no photons, just void area, space itself filled with an immense amount of energy at each place. This energy changed over time, extending in a short and determined fashion as the universe prolonged. These adjustments loosened as much as large extensions, even as new confined scale changes have been made to pinnacle them. This superposition of instabilities throughout scales is a characterizing element of cosmological extension. It would give up for arbitrary motives not planned. If you lived in an expanding universe, you would probably come across close by regions where an augmentation reached a conclusion, or the space amongst you and them extended emphatically. In short, you can attempt to recognize what happens in the direction of the beginning of a significant impact. Earlier, that area vanished completely from view. Before everything, it includes a small local region, perhaps no more enormous than a human-sized hamster ball, however probably extensively bigger. The power feature of space then receives changed over into matter and radiation. This change occurs quickly, taking kind of but not instant. As the power certain up in space itself changes over into particles and photons and more, the temperature quick augments from just a few degrees above absolute zero to perhaps around 20 Kelvin over the equal brief time frame. Because of the massive measure of electricity modified, everything actions near the speed of mild. All debris act as radiation with vast energy, whether they're massless or big. This modification is called reheating, marking the cease of improvement and the starting of the level called the recent massive bang. As development proceeds, you will witness a significant alternate from all preceding situations. When the hot huge bang starts off evolved, the increasing universe quick slows down. After the hidden photograph of development in an inflationary universe, space expands definitively, with greater a long way away regions going for walks unendingly. While improvement ends and the hot massive bang starts, more remote regions will recede from you to an ever-increasing degree. Regularly as time progresses, the part of the universe where improvement ends sees the extension charge drop, at the same time as the increasing areas surrounding it see no such drop. Underneath growth, the gap to any object could double after a short period, and whilst that same quantity of time elapses, that distance doubles again. Forever and ever, once the Big Bang starts off evolved, this changes because the expanding universe slows down after the preliminary moment of improvement. Before the Big Bang, you may come across improvement cleaning off with neighboring areas. These regions where an improvement ends will fill with count, antimatter, and radiation and increase more slowly than the still-growing areas, leaving you inside the increasing nearby as an average nearby within spacetime. Those areas wherein warm, huge bangs occur will become isolated from other places where development keeps. That means they'll quickly recede from each other's view inside the norm inflationary picture. Accordingly, the development charge modifications, there's little threat that any universes with separate warm Big Bangs will ever engage. The vicinity wherein we come to live receives fantastically lucky, and growth reaches a conclusion. For us, the energy characteristic of area itself gets changed over to a warm, thick, and almost uniform ocean of particles with the primary imperfections and departures from consistency referring to the quantum modifications that existed and had been loosened up across the universe at some stage in development. The high-quality energy quantum fluctuations correspond first of all to overdense areas, while the negative power fluctuations get changed over into initially underdense regions. Those serve as the seeds of huge structures. We cannot see those density fluctuations today as they were when the universe first of all went through the hot massive bang. There are not any visible imprints we will get right of entry to from that early period. The first observable imprint comes from around 380,000 years later after going through widespread affiliations, although we will extrapolate return to understand the preliminary density fluctuations, finding something steady with the narrative of galactic improvement. The temperature fluctuations are engraved on the cosmic microwave background, CMB, supplying proof of how the Big Bang started. However, there are many inconsistencies between the CMB and our present-day model of cosmology. We're missing something, and those can be summarized in 4 inconsistencies. First, on fantastically massive scales, the universe isn't behaving as anticipated. The light from the CMB is being lensed via count between us and the CMB. This indicates that count acts like a massive lens, bending and converting the amplitude of the mild behind it. The extent of this lensing isn't always steady with our modern-day model, representing a tremendous undertaking for cosmology. Second, the 2 sides of the equator of the CMB sky have different average temperatures, conflicting with the expectancy of uniformity in the universe's earliest stag. The assumption that the universe must have begun reliably ends in several inconsistencies. Third, the value of the Hubble constant, which describes how fast the universe is expanding, changes depending upon whether or not we degree it from the cosmic microwave background, CMB, or from neighboring stars. Together, these irregularities suggest we are lacking something important in how we interpret the universe. One proposed solution comes from loop quantum cosmology, which originates from loop quantum gravity. In this framework, gravity itself is made up of particles called quanta, shaping the fabric of existence. In loop quantum cosmology, there is a smallest scale of space, the Planck scale, or 1.0 times 1, 0, minus 35, 1.0 by 10, minus 35 meters. This means that the Big Bang couldn't exist in a universe defined by this theory. Instead, the universe might never reach an infinitely small, dense point near the Big Bang. In loop quantum cosmology, when the universe was very small, quantum corrections predict a repulsive force causing a bounce instead of a singularity. This suggests that our universe might have originated from a previous universe that contracted and then expanded again, similar to a phoenix rising from the ashes. While the idea of a cosmic bounce isn't entirely new, loop quantum cosmology provides a mathematical framework to support it. Cyclic time, like the idea of a cosmic bounce, is also present in Hindu cosmology, adding further weight to this idea. If loop quantum cosmology is correct, the early universe might have had high energy and density. This scenario might adjust the CMB, acting as mild differences in temperature across the sky. These variations, measured by the right energy spectrum, could provide significant evidence of the universe's origin and support the possibility of a bounce. Overall, loop quantum cosmology offers a compelling alternative to the standard Big Bang model, probably resolving some of the long-standing inconsistencies in cosmology and providing insights into the origins of the universe. It also offers a promising explanation for the third irregularity, the discrepancy in average temperatures between the two hemispheres of the CMB sky. The structure provided by loop quantum cosmology addresses the primary anomalies observed within the CMB, the unusual behavior at large scales, and the lensing effect. According to Dr. Venet Goind of the National Institute of Advanced Studies, the possibility that these irregularities are not just measurement errors but originate from quantum gravity effects occurring early in the universe is highly interesting. To confirm such claims, significant evidence is required. The idea that the universe started in a cosmic bounce has been proposed before, but its confirmation requires extensive research. Cosmic variance poses a challenge in this view, as our observations may be limited to specific elements of the universe, complicating our understanding. Dr. Dwayne Johnson, a co-author of a vast study and a professor at Penn State University, highlights the difficulty in validating such theories due to the significant diversity. But the incorporation of new possibilities like loop quantum cosmology and its extensive implications holds promise in resolving specific cosmological problems. Despite these advancements, a large question remains. Did the universe have a beginning at all? Proponents of the universe having a beginning insist that it did, but this raises questions about the nature of the event that started everything. Conversely, cyclic cosmology proposes an eternal universe, constantly undergoing cosmic bounces. However, physicist William Kenny of the University at Buffalo identifies a critical flaw in this idea: entropy. The degree of disorder in a system increases with every cosmic bounce, leading to a continuous depletion of usable energy. This entropy increase implies a beginning, like a Big Bang, conflicting with the idea of an eternal universe. While new cyclic models try to address this problem by including expansive phases between bounces to dissipate entropy, Kenny's research suggests that the universe probably had a specific beginning. Kenny's findings highlight the ongoing debate over cyclic universes, prompting further research into their feasibility. But proponents of cyclic universes have yet to address this criticism fully. The scientific communication about this topic continues to evolve, driven by the quest to determine the universe's origins and its ultimate fate. Quantum cosmology and cyclic models, which advocate various mechanisms to address anomalies, have sparked interest among cosmologists. Nelson dos Santos of the Brazilian National Institute for Space Studies, who has delved into bouncing and cyclic models, notes that while loop quantum cosmology bounces address some anomalies, they may not be fully useful. Still, he remains confident in the possibility of a cyclic universe. According to Nelson, the life of the universe is positive, making a cyclic universe invariably present seem more viable than one created at a particular moment. As a scientist, he remains open to exploring both opportunities. While the beginning of our universe remains a mystery, there has been intense discussion about its ultimate fate. The destiny of the universe depends on its composition, including dark energy and matter, determining its future. Essentially, there are two primary scenarios: endless expansion or contraction. In one scenario, the universe expands indefinitely, with stars eventually exhausting their fuel, leaving behind stellar remnants like white dwarfs and black holes. But the fate of the universe depends on the nature of dark energy, a mysterious force driving the universe's expansion. If dark energy remains constant, the universe's expansion accelerates, leading to a cold dark big freeze as matter disperses and entropy increases. Instead, if there is enough matter, the universe's expansion may slow and reverse into contraction. This scenario leads to the possibility of a cyclic universe model, where the universe undergoes cycles of expansion and contraction, never reaching infinite density or a specific beginning. Each cycle marks the beginning of a new era, providing a reassuring perspective compared to a cold, dark death. Regardless of the universe's fate, our presence at this particular moment is remarkable. It indicates our unique position within the universe and the essential role of knowledge in contemplating the universe's vastness and its inevitable reality. As we ponder the universe's nature, we're compelled to consider the meaning of our existence and the fleeting nature of time itself. Thank you for listening to this episode. Your support drives us to deliver quality content, and we appreciate your feedback on today's topic. Stay tuned for future episodes by subscribing and spreading the word. Until next time, keep exploring the mysteries of the universe.